everybody. Today we are going to be talking about forces. Most of us have heard the word forces used before, but we might not know what it actually means in the physics world. Before we get started, these are your homework questions for tonight. Make sure you read the page that is associated with this video. It's titled, "What is a Force?" and answer the following questions. If 1 Newton is equal to 1/4 of a pound, what is your weight in newtons? Number 2, draw a free body diagram for something in the room you are working in. A, first draw a picture of the object, and B, then draw the free body diagram next to it. Make sure to name all of the forces. So once you've finished watching this video, make sure to come back to this point in the video and answer your questions for the next class. So what is a force? It's actually really simple. A force is a push or a pull. That's all it is. An object at rest needs a force to get it moving. So if this car in this picture is at rest, it's not going to go anywhere unless somebody pushes it. It's just going to sit there. On the other hand, a moving object needs a force to change its velocity. So these guys down here playing tug of war, if they want to change the velocity of the other team so that they can have the advantage, they need to apply a force. They need to pull. There are 4 fundamental forces in the universe as far as we know. 2 of them you're probably pretty familiar with, and the other 2 not so much. The first one is gravity. We all interact with gravity all the time. And when we think of gravity, most of the time we think of gravity being what keeps us on the earth, and it keeps us from floating off into space. Turns out it's a little more complicated than that, but we'll get to that later. Second force is electromagnetism. If you've played with magnets before, that's electromagnetism. If you've ever shocked yourself on a doorknob on a dry winter's day, that's electromagnetism. The electricity flowing through the computer into this smartboard so that I can make this video is electromagnetism. The third force is called the strong force, and it's what keeps the nucleus of atoms together. Technically, all of the little protons in the nucleus are repelling each other. They want to get away from each other as far away as they can, but they don't fly apart. The reason they don't fly apart is the strong force. And finally, we have the weak force, and this is what's associated with radioactive decay. We will generally place forces into 2 broad categories: contact forces and field forces. Just like it sounds, contact forces are forces that require physical contact between 2 objects. Examples of this are kicking a ball. When you kick a ball, there is a physical contact between your foot and the ball. Another example is friction. When you rub your stocking feet over a carpet, there's friction because you have physical contact between your socks and the carpet. Third example is this right here. This boxer is punching another guy in the face. So there's physical contact between that man's face and the other one's glove. That is a contact force. Field forces are a little more strange. They're forces that act over a distance without any physical contact. So things don't need to be touching for a field force to be present. Examples of this are the magnetic force and gravity. So if you are standing on a diving board and you're about to dive into a swimming pool, when you jump off that board, gravity pulls you toward the pool. You don't have to be in contact with the earth for gravity to be working. It works over the space. Same with the magnetic force. You don't have to have a magnet stuck straight to the refrigerator to get it to work. You can pull it a little bit away from the refrigerator and it will still be attracted. A couple more facts about force. Force is a vector quantity, and we already talked about vector quantities and what they are. So you should know by now that it means it has a magnitude as well as a direction. So it not only matters how strong your force is, but what direction it's pointing in. The unit of force that we use is the Newton, and it's based on this guy, Sir Isaac Newton, arguably one of the most important physicists that we've had. And the Newton, which is abbreviated with a single capital N, not lowercase n, capital N, the Newton will be the first compound unit we learn about. And a compound unit is one unit that's actually made up of two other units. So 1 Newton is equal to a kilogram times a meter per second squared. So when we break down a Newton into its constituent parts, it is a kilogram and a meter per second squared. These units right here should be tipping you off as to how we solve for a Newton, but that comes in the next lecture. So what exactly is a Newton? In America, we measure a lot of things in pounds. So we have a good feel for how much 1 pound is or 20 pounds is, but we don't really have a good feel for a Newton. So what you do is take one of these delicious looking quarter pounder with cheeses. You take off the top bun, scrape off the ketchup, mustard, pickles, onions, and cheese, lift the patty off the bun, and that is a Newton. In other words, a Newton is about a quarter of a pound. In the British system, the unit of force is the pound, and that's also what we use in the United States. So when we say, I weigh 400 pounds, I'm not telling you my mass. I am actually telling you the force with which gravity pulls me to the earth. When we have lots of forces acting on an object, it can get really confusing. Remember, from the first slide, in order to get an object moving or to change its motion, we need to apply a force. But if we have tons of forces being applied, how are we going to know in what direction we're going to change that object's motion? What we need to do is add all of the force vectors together to determine a single resultant or net force that acts on the object. So the net force is what remains if you add up all of the forces acting on an object. One of the most useful tools in physics we use for solving force problems is called the free body diagram. And that is this guy right here. This is a free body diagram. A free body diagram is used to isolate the object, take it away from the system and everything around it, and get it all by itself, and show only the forces acting on that object. They're pretty easy to draw. All you have to do is make a dot, and this represents whatever the object is. In this case, this dot represents an airplane. After you make your dot, you use arrows to represent force vectors of what forces are acting on that object. So for this picture, we have an airplane, and it's flying, and we want to know what the net force is on this plane. So we draw the dot over here, which represents the plane's mass, and we add forces. Gravity is always pulling down, so we have the force of gravity here. It's propelling itself forward with the engines, so we have the force of the thrust from the engines pointing forward. It's running into some air resistance that's keeping it from moving too fast. So we have air resistance pushing back on it. And of course, if we didn't have lift, this plane would crash straight into the ground. It would be a very poorly designed plane. So we have the force of the lift keeping it in the air. So let's do a few examples. draw a free body diagram for someone standing on the earth. Especially in the beginning, a good way to start these kinds of problems is to draw a picture. So we can draw the earth and a little person standing on the earth. Actually, this is a gigantic person, but just for the sake of the drawing. That is our person standing on the earth. We want to make a free body diagram of this person. So we take the center of their mass and we represent it using a dot. Then we want to add arrows that represent the force vectors acting on this person. So this person is standing on Earth, which means they are being pulled down to the center of the Earth by gravity. And I'm going to write that FG. So that means the force of gravity pulling them down. But they're not really moving toward the center of the Earth where they're being pulled. Something is keeping them from moving toward the center of the Earth, even though they're being pulled in that direction. And that is the Earth pushing up on them. So this is the force of the Earth physically pushing up on them. The force of gravity here is a field force. But the force of the Earth is a contact force. The Earth can't push up on someone if we're not touching it. Number 2, draw a free body diagram for a football as it's being thrown. So we have our little oddly shaped football here, and an arm with someone holding it, and this person is just about to throw it. So we represent our football, our object, as a dot, and we want to add our forces being applied. So a force that always acts on things when we're on Earth, in Earth's atmosphere, is gravity. So even though this ball is being held up by this person, it is still being pulled down by gravity. So we have the force of gravity. The reason it's not falling is because the person is pushing up on it, right? Well, the person, if they're throwing it, is also trying to move it forward. So their force of their throw is going to be kind of at an angle. The person is pushing up on it a little bit here to keep it from falling to the ground because gravity's pulling on it, but they're also pushing it forward so that when they release the ball, it moves forward. So when you add these two little green dotted forces up, the result is the force of the throw. And number 3, draw a free body diagram for the same football right after it leaves the quarterback's hand. So this is an easy drawing because really all it is a football. Nobody's touching it, it's flying through the air. Easy, right? Well, we have to represent the football by a single dot and add our vectors. So what's always acting on an object when it's on Earth? Gravity. So it's being pulled down by gravity. Is there anything else acting on it? It's moving forward, but is there anything physically pushing this thing right now? No. There are no pushes or pulls other than the force of gravity acting on this football. So the football will continue to move forward, but there are no more forces acting on it at this point other than gravity. So go ahead and go back to the beginning of the video where the homework questions are and try and answer those the best you can and turn those in at the next class.